Okay, this is your video for 5.4. I just want to kind of recap from yesterday up front. Remember yesterday we talked about a median, and a median is a segment that goes from one vertex to the midpoint of the other side. And when you have three medians that intersect, they intersect in that centroid, and we got that centroid theorem, that 2/3, 1/3. So this centroid is made up of medians. Then we also had altitudes, where you have the vertex to the perpendicular point on the other side, the vertex to the perpendicular point on the other side, the vertex to the perpendicular point. Those are all made up of altitudes, and together when they intersect, you find the orthocenter. Okay, and what we're going to learn about today is a midsegment. So from your vocabulary grid, you can see that a midsegment is when you take the midpoint of one side and connect it with the midpoint of the other side. That's a midsegment. So we have medians, we have altitudes, we have midsegments. Now, every triangle has three midsegments, but instead of intersecting in one place like the centroid or the orthocenter, they don't intersect all together. They come together to form another triangle inside the other triangle called the midsegment triangle. So here's a bigger example of that here. You can see X is the midpoint of QP, Y is the midpoint of QR, and Z is the midpoint of PR. So I have three midsegments, XY here, YZ here, and XZ here. And when those three all come together at the same time, they form a triangle inside the original triangle, triangle XYZ, and that triangle is called the midsegment triangle because it's made up of the three midsegments. We are going to talk about Sierpinski's triangle tomorrow in class. I'll show you a little demo of that. Alright, this first example we're going to do here is actually a coordinate proof of the triangle midsegment theorem that you're going to have on your vocabulary grid. Remember from chapter 3 that a coordinate proof is where you solve everything out and you work everything out using algebra, but you explain what you're doing at the end, and that's just your proof. Okay, so I have the vertices of triangle XYZ here. M and N are the midpoints of XZ and YZ. So let's stop here and let's find M and N. So I'm going to start with X at -1, 8, and how about Z rather, at 3, -4, and I'm going to find the midpoint at 1, 2, and I'm going to call that point M. So I'm going to go to 1, 2, and I'm going to call that point M, the midsegment of X and Z. Same story with Y and Z. Y is at 9, 2, Z is at 3, -4. Add them up, divide by 2. Point N is going to be located at 6, -1. And that will be the midsegment of YZ, and the midpoint of YZ. Sorry. So when I connect M and N, I form the midsegment MN. So this is just drawing the diagram that we just had. Now we're going to prove special things about the midsegment. The first thing we're going to prove is that this midsegment MN should be parallel to the segment across from it. Not the one that you use to form the midpoints, but the one that has been untouched so far, X, Y in this case. So parallel means same slope. So we're going to start by finding the slope of MN, doing rise over run. So from 2 to -1, I went down 3 places. And for your run, from 1 over to 6, I went over 5 places. So the slope of MN is -3/5. I'm going to do the same thing for XY. So from 8 down to 2, I went down 6 places. And from -1 all the way over to 9, I went over 10 places. So when I reduce that, that reduces down to -3/5 as well. So you know that if things have the same slope, that must mean they're parallel. So I just proved that MN is parallel to XY by proving that they have the same slope. Okay, so halfway done, these two lines are parallel. The second part says that I need to prove that MN is half the distance of XY. So we're going to do distance or Pythagorean theorem, whichever you prefer. Now, Pythagorean theorem works out being easier here, and we also saw when we were doing all that in chapter 3 with lines that I could use the coordinates from the numbers from the rise over run, and I could use that for my Pythagorean theorem, and we know that works out because I just figured out that this went over 10 and down 6. So those are the two sides of your Pythagorean theorem. A squared plus b squared is equal to c squared. So really, after I found the slope, I kind of have this halfway done already. So let's start with MN. I'm going to do Pythagorean theorem with 3 and 5 because that is my rise and my run. I don't really have to worry about the negative because I'm just about to square it anyway. So negative 3 squared, it doesn't matter. It's all 9 plus 25, which is the square root of 34. And that doesn't break down because that's going to hit you with 17 in a second. So we don't have to break that down. Now let's do xy. Okay, so xy we have 6 and 10. It's important that if you're going to use the slope that you use the unsimplified slope. So we have to use the 6 and the 10 or we won't get the right distance. So that is 36 and 100. So the square root of 136 is going to break down. And that's going to be 2 and 68. 2 and 34. We already decided 34 doesn't break down. So this is going to be 2 square roots of 34. Now this is actually simple to leave this in the radical form because it proves exactly my point, what I wanted to prove. If this one's the square root of 34, then this one's twice the size. So it's very easy for me to turn around and say, hey, MN is half the distance of XY because I doubled it. So I did my coordinate proof to prove the two things about a mid-segment, both and the opposite side, both that they're parallel and that the mid-segment is half the distance of the other side. Okay, so that was a lot of work. So you might want to go back and rewatch that video, that example right there, because that was a lot to take in all at one time. But what that brings us to is your mid-segment triangle theorem that's on your vocabulary grid. So stop and look at that for a second, and it says exactly what we proved here, but for any triangle, that the mid-segment will be parallel to the opposite side and it will be half the distance to the opposite side. So this coordinate proof proved our triangle mid-segment theorem. So it was a lot of work, but it was worth it. Okay, so let's do an example with that here. So BD, so I want to find BD. Well, I can tell that BD is the mid-segment of this triangle because B is the mid-segment here, midpoint here, D is the midpoint here. So that means that it is parallel to the opposite side AE and half the distance. So if AE is 17, then BD would just be half that. So 17 halves by the triangle mid-segment theorem. Now you could go and change that to a decimal, but why bother? It's already ready. Okay, then the second one, B, says to find AF. Now AF doesn't have anything to do with a mid-segment. I can do this by the definition of the midpoint. I could have done this back in chapter 1. If F is the midpoint of AE, then each of the pieces are just half the distance, which this shows us something that we haven't talked about a mid-segment. So it's half the distance of the other side, but so are from the midpoint to each vertex. So actually, the mid-segment is congruent to the half points over there. So AF is congruent to FE, which is also congruent to BD. And this is going to be true all the way around the figure. CD is congruent to DE, which is also congruent to BF. And then lastly, AB is congruent to BC, which is also going to be congruent to its mid-segment, DF. So that kind of shortens things for us later on, actually right now. So then C, we're looking for CA, which CA is the entire distance all the way across here. So I'm going to look over to his mid-segment, DF, which is 6.2. So if this is 6.2, then each of these is 6.2. So that means the whole thing all the way across is 12.4 by the triangle mid-segment theorem. Okay, so those are all the side lengths, any relationship that you could talk about, halfway, mid-segment, going backwards to double it. Now let's talk about the angles. So this is asking us to find the measure of angle CBD, which is this angle right here. Now, the only other angle that I'm given information for is this angle FDB right here that I know is 26. So I want to see how these are related. Now, the other thing that we talked about, mid-segments are half the distance, but the other thing we know is that they are parallel to the opposite side. And we know when we hear parallel, it's for a reason. We need to start thinking alternate interior, corresponding, all those kinds of things. So it's hard to see with all these mixed in together, but if you will kind of highlight and extend, maybe even redraw, you can see this mid-segment is parallel to the opposite side, and here's your transversal. So if you want to draw that by itself, you can see it like this. Parallel lines, the mid-segment and his opposite side, cut by the transversal right here. They're asking me for this. They gave me that this was 26. So when you kind of highlight the important parts, it's very easy to see, oh, hey, these are this is the triangle mid-segment theorem, gave me that these are parallel, and you knowing that they're parallel, the alternate interior angles theorem will tell me, hey, if this is 26, then this is also 26. So kind of two steps there. Make sure that you can see this this alternate interior here cut by a transversal. Okay, last one. In an A-frame support, the distance PQ is 46 inches. So let's label that. PQ is 46 inches. What is the length of ST if S and T are the midpoints of the sides? So S is the midpoint here. T is the midpoint here. So by definition of a mid-segment, I know ST is a mid-segment. Therefore, by the triangle mid-segment's a long word. By the triangle mid-segment theorem, I know that ST is half the distance of PQ. Therefore, ST is 23 inches. Okay, you are explaining this, so you do need to write all of this down, including your now margins and summaries that you're ready to do. Okay, see you tomorrow.